Hi dear students, this is Sononi, Assistant Professor, Department of Chemistry, Arts, Commerce and Science College, Jawahar, District Palghar. Dear friends, in the last part of the video of this molecular spectroscopy, we have studied about the vibrational spectroscopy with the different conditions. We also studied about the numerical based upon the vibrational spectroscopy. Dear friends, in this part of the video, we are going to talk about the vibration-rotation spectra of the diatomic molecules. Here before this we also studied about the rotational spectroscopy, and here in the rotational spectroscopy we have studied that the pure rotational spectra is observed because of absorption of micro radiation, while vibrational spectra is observed due to the absorption of IR radiation. And we have studied both these two spectra separately with the help of diatomic molecule. Here in this topic, now we will consider a molecule, or we will consider a system or the model in which simultaneously the rotational and vibrational motion can be studied, and such a system in which the rotations and vibrations can be studied simultaneously. Such a system is called as simple harmonic oscillator undergoing rotational motion. Generally, the system which shows the vibrating motion is called as harmonic oscillator, but it shows the rotational motion also. That's why it is called as the rotating vibrator or rotating vibrating rotor. So this is very simple. A diatomic molecule having behaving like a vibrating rotor absorbs IR radiation to undergo vibrational transitions accompanied by rotational transitions. So here this is the diatomic molecule which behave as a vibrating rotor, absorbs IR radiation, and it will undergo vibrational transitions as well as rotational transition. So this vibrational and rotational motion take place quite independently, and hence the total energy of the molecule is simply the sum of vibrational and rotational energies. So the total energy of this vibrating rotor is the sum of vibrational and the rotational energy. Dear friends, here in the rotational and the vibrational spectroscopy we have studied about the selection rule. Based upon the same, whenever the radiation is absorbed by a molecule, it is found theoretically as well as experimentally that transition always occurs between certain energy levels, and these results to what is known as selection rule. So for harmonic oscillator rigid rotor, the selection rule is given by, or the selection rule for vibrational quantum number and the rotational quantum number is delta J plus minus 1, and delta V is also plus minus 1. So this is the two conditions. So for vibrational rotational spectroscopy, the selection rule is delta J is equal to plus minus 1, and delta V is also plus minus 1. So under this condition, if delta V is equal to plus 1 and delta J is equal to plus 1, the spectral lines are obtained and these are clumped together, known as R branch lines. So under the condition delta V is equal to plus 1 and delta G is equal to also plus 1, the whatever spectral lines are obtained, these all spectral lines are called as R branch lines. And when delta V is equal to plus 1 and delta J is equal to minus 1, then the whatever spectral lines are obtained, these are clumped together, called as P branch lines. So this is the condition for R branch lines and the P branch line in the vibration rotation spectra. So here for these two types of the lines of the branch, we are able to determine the frequency of these lines. So already we have the equation for the energy, vibrational energy V plus 1 by 2 S omega bar, that already we discussed in the vibration spectroscopy. And the rotational energy of the rotational energy level is given by the S square upon 8 pi square into I into J into J plus 1, that already we discussed in the previous two types of the spectroscopy separately. Here omega bar is the oscillation frequency in terms of mu is the vibrational quantum number, V is the vibrational quantum number, and J is the rotational quantum number. So in order to obtain the total energy of this vibrating rotor is the sum of vibrational and the rotational energy, in which we will consider transition from V single prime to V double prime and J single prime to J double prime by putting the values of V single prime, J single prime and V double prime, J double prime. These are the equations for this. And definitely delta E is the total energy in final state minus total energy in the initial energy level. So by making the simplification of this, definitely we will consider this equation. So there is delta V, difference between the two energy levels, plus minus 1 and plus minus 2. So applying this condition, if we consider delta V is equal to plus 1 and delta G is equal to plus 1, we will get the energy difference between these two. And according to the Planck's quantization of energy, delta V is equal to C into mu bar. And after simplification, definitely it is not important for you, but we will get the final frequency, that is omega bar plus 2b into G double prime. And under the another condition, delta V is equal to plus 1 but delta G is equal to minus 1, again we will get another frequency, mu bar is equal to omega bar minus 2b into G single prime. So finally, in this case, the first term omega bar represents the original center of vibrational band, and the second term indicates the rotational lines associated with the vibrational band. So for this, delta V is equal to plus 1 and delta G equal to plus 1, we got this frequency, and therefore the rotational lines are on the higher side of the frequency and they constitute the lines called as the R branch lines. So under this condition, so this is the frequency for R branch lines, and definitely we will consider different transitions. So we are getting for J is equal to 0 to 1, we are getting the first line R0, 1 to 2 R1, 2 to 3 R2, 3 to 4 R3. In this way we are getting different R lines. So for another condition, delta V is equal to plus 1, delta G is equal to minus 1, so the omega bar minus something, so definitely it is on the lower side of the frequency and gives lines called as the P branch lines of rotational and vibrational spectrum. And 1 to 0 it will be P1, 2 to 1 it will be P2, P3, P4. In this case, in this way we are getting different P lines of the P branch line, and this is the spectrum. Here this is the center. On the lower side there will be P branch line, and on the higher side there will be R branch line. So for this, definitely delta V is equal to plus 1, delta G is equal to also plus 1, and for this definitely delta V is equal to plus 1 but delta G is equal to minus 1. And this is the case that we here that we'll talk. So here, dear friends, we discussed about the vibrational rotational spectrum of the rigid diatomic molecule, means the vibrating rotor, in which the diatomic molecule acts as the, or it shows the simple harmonic motion oscillations, and it is simply called as simple harmonic oscillator. So for that, delta V is equal to plus minus 1. But here we will talk about the other type of the oscillator, in which definitely the selection is going to change, and in this case the diatomic harmonic oscillator are those molecules which satisfy the selection rule, where the vibration energy levels are equidistant, that we already discussed in the vibrational spectroscopy. In such molecules, small amount of energy is absorbed and hence the distortion of bond is smaller. In other words, restoring force acting on the bond is stronger, and the restoring force of harmonic oscillator is directly proportional to displacement, and the energy of the harmonic oscillator is given by this equation. Okay, so the potential energy, again that's why this potential energy curve for such system is a true parabolic in shape, and hence dissociation of molecule is difficult. But in practice, molecule does not always vibrate as simple harmonic oscillator, and some molecule absorb large amount of energy, hence the amplitude of oscillation increases, and hence the restoring force becomes weaker, and the atom of molecule may fall apart from each other. Such a real oscillator is called as anharmonic oscillator. The energy levels are no longer equally spaced, but these are grow closer as value of V goes on increasing, and that's why the modified equation for the anharmonic oscillator is given by this, including by the term A, and this A is called as anharmonicity factor, and it is given by the V plus 1 by 2 bracket square. Here C omega bar into X, and this X is called as the anharmonicity constant. So this is the anharmonic oscillator I have here, and this is the energy for the anharmonic oscillator. So in this case we will be able to get the frequency, but in this case the selection rule for anharmonic oscillator is not delta V is equal to plus minus 1 only. So it shows the different selection of delta V is equal to plus minus 1 also, plus minus 2 also, and the plus minus 3. So under this condition, under the delta V is equal to plus minus 1 means V is equal to 0 to 1, the energy is given by the equation omega bar into 1 minus 2x, and this vibrational band produced due to the transition from V is equal to 0 to 1 means delta V is equal to plus minus 1. The band is called as the fundamental band. So for the delta V is equal to plus minus 1, the whatever frequency or the vibrational band is obtained, it is called as the fundamental band, or it is simply called as the first harmonic band. Under the second condition, delta V is equal to plus minus 2 means V is equal to 0 to V is equal to 2. The whatever frequency is given by this equation, and the whatever vibrational band due to the transition from V is equal to 0 to 2 is obtained means delta V is equal to plus minus 2. This vibrational band is called as the first overtone, or it is also called as the second harmonic band. Again, for the another transition from V is equal to 0 to 3 means delta V is equal to plus minus 3. The whatever frequency, this is given by this, and this is for the delta V is equal to plus minus 3, and the whatever vibrational band is produced, it is called as second overtone, or it is simply called as the third harmonic band. And the relation between these two, first, second, third harmonic band, is given by this equation. So these are in the ratio of 1:2, 1:2, 2:2, 3. So this is the fundamental band and different overtones in on a harmonic oscillator. So this is simple case. The spectral line appearing due to the transition from V equal to 0 to 1 are called as the fundamental band or first overtone. Sorry, fundamental band or first harmonic. The transition from V equal to 0 to 2 gives the line called as the first overtone or second harmonic, and the transition from V equal to 0 to 3 produces small spectral line called as second overtone or third harmonic. In this way, we are getting different harmonic. There are various applications of this vibration rotation spectrum, and the first one is the determination of force constant. Here, the diatomic molecule considered as the simple harmonic oscillator, and in simple harmonic oscillator, it always obeys the Hooke's law, and according to Hooke's law, restoring force is directly proportional to displacement. Negative sign indicates these are acting in opposite direction. X is the displacement, okay, and this here it is observed that this K is called as force constant. Force constant of bond is the measure of force required to stretch or compress the bond. If greater is the force constant, indicates the greater is the strength of the bond, and it is found that this vibrational frequency of the molecule is given by the equation, that is omega bar equal 1 upon 2 pi s into k upon mu. Means vibrational frequency is related to the force constant K by this equation. Mu is the reduced mass of the molecule, and to calculate the K, definitely we have this equation, and mu is nothing but the reduced mass. So in this case, so the significance of this force constant K is given by this equation, and it indicates that omega bar is directly proportional to the force constant. Under root of force constant means the oscillation frequency of the molecule increases with the increasing force constant, and it indicates that the higher the value of force constant K, greater is the bond strength and hence bond energy. So therefore bond energy of HF molecule is greater than that of HI molecule, therefore HF cannot be easily oxidized. Again, the molecule involving the multiple bond between the atoms always have higher value of force constant and hence greater stability. Greater the force constant, greater will be bond order and smaller will be bond length. So this is again important. So force constant is directly proportional to bond order but inversely proportional to bond length. Therefore force constant is inversely proportional to bond length. And there are some different examples actually. Bond order, and definitely force constant, here it is smaller, here it is greater, and here it is greater. Here bond length is greater, bond length is smaller, and in this case it will be smallest, and this is related to this force constant. So hybridization also affects the force constant of bond, and these are in the ratio of sp is greater than sp2, which is greater than sp3. So this is the again triple, single, and the double bond. The force constant or the force constant can be used to check the possible resonance structure, because here there is what there is for the single bond, the force constant expected for constant 490. For the double bond, it is 1280, and for the triple bond, definitely this 1860. But in the CO2 molecule, it is 1520. So it is in between. It is in between carbon carbon double and the triple bond, and this value is in the between of carbon oxygen double bond and carbon oxygen triple bond, and that indicates that it has the intermediate structure of carbon oxygen double bond and carbon oxygen triple bond, and this is only possible due to the resonance in carbon dioxide molecule. So this is also another significance of this first constant. So this vibration rotation spectra also used to determine the internuclear distance between the atom. The frequency separation between the two consecutive p branch or the r branch lines is given by the 2b, and you know where 2b is equal to 1 upon h upon 4 pi square I into c. Therefore this b will be equal to h upon 8 pi square I into c, and delta mu, you know, delta mu is equal to 2b, and definitely from this we will be able to calculate the I, and from the I definitely we will be able to calculate the internuclear distance small r. This is very simple by this equation. Again, isotopic effect. With the help of this isotopic effect, we are able to compare the bond between the atoms of higher masses than that of the lighter masses. It is also observed that bond between the atoms of higher mass will vibrate at lower frequency than the bonds bearing lighter atoms, according to this, because your vibrational frequency is inversely proportional to the reduced mass. That's why vibrational frequency will be inversely proportional to mass of the atom. So this is another thing from which we will be able to calculate the isotopic effect, whether the atoms are heavier or lighter. That can be studied with the help of this vibrational frequency. So dear friend, these are some significance of this vibrational rotation spectra, or the vibrational rotational transitions in the molecule. So in this lecture we try to discuss about vibrational rotational spectroscopy of the rigid atomic molecule, as well as the significance of vibrational rotational spectroscopy. So this is very important regarding with this molecule. So dear friends, in the next part of the video we will try to discuss about the Raman spectroscopy or the Raman spectra, and definitely that is very important in the study of molecular spectroscopy. So we will resume again here in the next part of the video to discuss about the Raman spectroscopy and different modes of vibrations in H2 molecule, in the water molecule, as well as carbon dioxide molecule. And definitely we will also discuss about the Raman spectroscopy, and with the help of Raman spectroscopy as well as IR spectroscopy we will discuss about the rule of mutual exclusion. So dear friends, we will resume in the next part of the video. Thank you very much.